Well, hello everybody, and welcome back to North Country Ham. Name is Aaron, KD2RSS, and today I'm going to be doing a little more, some more questions out of our extra class handbook here by Mr. West. So stick around. Let's get right into it here. All right, so you can see here a little bit of blinding light, but got our 2020-2024 extra class book we've been doing questions out of, and we're just going to continue on where we're left off the last video and do another 10 to 15 questions and see how things go. So let's get right into it here. We're kind of into a chapter on amps and power supplies, as you can see. So our next question we're on is, why are switching amplifiers more efficient than linear amplifiers? Is it A, switching amplifiers operate at a higher voltages? B, the power transistor is at saturation or cutoff most of the time? C, the linear amplifiers have high gain resulting in higher harmonic content? Or D, switching amplifiers are push-pull circuits? The speed at which an active device switches from the fully on to fully off state determines its efficiency. In either state, the device dissipates zero power. The only time heat is concentrated is during the transition. The faster the transition can be made, the less the heat. Because the power transistor is at saturation or cutoff most of the time, the transition can be made almost instantaneously. Switching amplifiers can approach 95% efficiency at audio frequencies. Such performance has not yet entered the high power RF realm, but getting there. So the correct answer is B. So why are switching amplifiers more efficient than linear amplifiers? Answer B, the power transistor is at saturation or cutoff most of the time. I hope those of us that have was able to make it down to Florida for Hamcation is enjoying it and having a good time down there. And I hope everybody, I don't know who's intending on watching the Super Bowl, but being here in a little bit, hopefully it's a good game. I know my wife's excited being from Ohio. She's pretty happy to see the Bengals there. What is one way to prevent thermal runaway in a bipolar transistor amplifier? A, neutralization. B, select transistors with high beta. C, use a resistor in a series with the emitter. Or D, all of these choices are correct. UHF and microwave operators who homebrew their own amplifiers are cautious to protect against transistor thermal runaway. Adding a fixed emitter resistor may cut down slightly on the transistor voltage gain to control transistor current without sacrificing linearity. In tube equipment, this is called a cathode degeneration. In your transistorized amplifier, thermal protection is provided using degenerative emitter feedback through the use of a resistor R3 in the diagram in a series with the emitter to ground. So the correct answer is C, and it kind of shows a little bit of a diagram here and a little bit of a formula for the stuff, and it kind of shows it in a picture for the emitter. So what is one way to prevent thermal runaway in a bipolar transistor amplifier? Correct answer is C, use a resistor in a series with the emitter. And we're learning things now. All right, our next question here. What devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of a transistor HF amplifier? A. Electrolytic capacitors, or electrolytic, I'm sorry. B. Butterworth filters. C. Ferrite beads. Or D. Steel core toroids. Put that behind there. If you look into the modern VHF, UHF, single band or dual band amplifier, you'll see many leads dressed with small ferrite beads to minimize parasitic coming down voltage or control lines. Correct answer is C. So what devices are commonly used as VHF and UHF parasitic suppressors at input and output terminals of a transistor HF amplifier? Correct answer is C. Ferrite beads. All right, moving right along. So we got a few people in here with us, so thank you for joining. Feel free to pop into the chat or throw some answers out there as we're reading along. I'll try to pay attention, and we'll see if any of us are guessing right. So, next question here. What is the effect of intermodulation products in a linear power amplifier? A. Transmission or spurious signals. B. Creation of parasitic oscillations. C. Low efficiency. Or D. All of these choices are correct. The effects of intermodulation, abbreviated IM, are spurious signal products usually traced to power amplifier stages or linear amplifiers with correct bias settings. Old-time hams called any station with strong IM products monkey chatter that may travel up to 200 kilohertz up and down the band from the main transmitted signal. As a new extra, with the new power amplifier turned on, start out on extremely low power input to the amp and suspect IM if any station drops down to your frequency and tells you that your signal is wide, splattering, and you should sound like monkey chatter. With careful tuning and monitoring of amp input drive power from your transceiver, intermodulation can be usually solved without having to completely field strip your station for repair. So the correct answer is A. How's it going tonight, Greg? I see you pop in there. Yeah, I've myself probably about the same timeline as you. I want to say, well, it's been just over a year for me, because I believe it was 2020 or August of 2020, maybe. I think I took my test. So, what is the effect of intermodulation products in a linear power amplifier? Correct answer was A. Transmission of spurious signals. Well, Greg, I don't know if it'll help, but I've got an entire playlist with all the questions so far. You can see I've gone through out of this new extra class book. This is like the 18th video. I'm doing probably 10 to 15 questions a video, so I don't know if you've seen them or not, whether it may help you or not, but pretty much all I've been doing is what you're seeing, going through question by question. So, all right, our next one here. What is the dropout voltage of an analog voltage regulator? A. Minimum input voltage for rated power dissipation. B. Maximum output voltage drops when the input voltage is varied over its specified range. C. Minimum input to output voltage required to maintain regulation. Or D. Maximum that the output voltage may decrease at rated load. Unlike switching regulators, analog regulators can only reduce voltage from unregulated value. This means you need to have a bit more voltage going into the regulator than you want at the output. Typically, you want the input voltage 30 to 50% greater than the output voltage for reliable regulation. Correct answer is C. Oh, well, thank you, Greg. Appreciate you watching. Hey, well, thank you also, the D. Welcome. So, correct answer being C. What is the dropout voltage for an analog voltage regulator? Minimum input to output voltage required to maintain regulation. Well, I appreciate you guys watching along and following the videos. It's always nice to see and hear. I do appreciate it. Oh, our next one here. Last one on this side of the page anyways. Make sure we can get these in here. How does linear electronic voltage regulator work? A, it has a ramp voltage as its output. B, it eliminates the need for pass transistor. C, the control element duty cycle is proportional to the line or load conditions. Or D, the conduction of control element is varied to maintain constant output voltage. Linear electronic voltage regulator varies the conduction of a circuit in a direct proportion to variations in line voltage to or the load current from the device. You will find a sophisticated voltage regulation circuit inside your base station power supply. So the correct answer is D, and it kind of shows it there a little bit. A pair of 3-terminal regulators for dual voltage power supply. So how does a linear electronic voltage regulator work? Correct answer D, the conduction of control element is varied to maintain constant output voltage. Yeah, I wanted to get on here for a little bit tonight, go through some more questions. I've been busy playing with the 3D printer and making things and designing some stuff. I've got some nice projects upcoming that I think are pretty neat. Hopefully one of the next videos will kind of show some of that instead of just doing the studying. So that's some of the upcoming. Always like building and DIY stuff. I like doing that, making stuff for the ham radio hobby. So next question here. What device is typically used as a stable voltage reference in linear voltage regulator? A, a Zener Diode. B, a tunnel diode. C, an SCR. Or D, a variactor diode. A Zener Diode is primarily, hopefully I'm saying that right, is primarily used as voltage reference. You can recognize the symbol for a Zener by the zigzag bar used in its schematic symbol instead of the straight line designated the cathode of a standard diode. Remember, zigzag equals Zener. A Zener diode is normally operated backwards in the normally non-conducting direction. At a very precise voltage, the Zener will conduct in the reverse direction, becoming a low resistance. A Zener can serve as a voltage regulator by itself or as a voltage reference for more elaborate voltage regulator. Before Zener diodes were around, the voltage reference of the choice was a gas-filled tube. Correct answer is A, and it kind of shows a breakdown of it there a little bit for a Zener diode. So what device is typically used as stable voltage reference in a linear voltage regulator? Correct answer A, a Zener diode. How many we get? Okay. What are we doing time-wise? Oh, not bad at all. Moving right along, folks. Our next one here. What is a characteristics of a switching electronic voltage regulator? A, the resistance of the control element is varied in direct proportion to the line voltage or load current. B, it is generally less efficient than a linear regulator. C, the controlled device duty cycle is changed to produce a constant average output voltage. or D, it gives a ramp voltage as its output. The switching voltage regulator actually switches the control device completely on or off. So, what is the characteristic of a switching electronic voltage regulator? Correct answer C. The control device's duty cycle is changed to produce a constant average output voltage. There we go. Alright, which of the following types of linear voltage regulator usually make the most efficient use of the primary power source? A series current source, B, a series regulator, C, a shunt regulator, or D, a shunt current source. The very common series voltage regulator is used in many high-power linear power supplies. With no load, the series regulator dissipates essentially zero power, while under full load it can dissipate up to 50% of the total power. And by contrast, the lower power applications, the shunt regulator is generally simpler. However, the shunt regulator dissipates the same amount of power regardless of the load. While the series regulator power loss depends on the current draw, with no load, the shunt regulator is 0% efficient. So the correct answer is B. So which of the following types of linear voltage regulator usually make the most efficient use of primary power source? Correct answer B, a series regulator. Moving right along here. Let me kind of move this up a little bit. There we go. What is the equation for calculating power dissipated by a series linear voltage regulator? A, input voltage multiplied by input current. Input voltage divided by output current. Voltage difference from input to output multiplied by an output current. Or output voltage multiplied by output current. So, move this back down here. Linear or analog voltage regulators are very clean, but they can be quite inefficient. A linear voltage regulator must always have a supply voltage significantly greater than the desired output voltage. In many high-power regulated supplies, as much as half the supply voltage is dropped by the regulator circuitry, which typically includes large series pass transistors mounted on massive heat sinks. As in any series circuit, the power dissipation of any component is equal to the voltage difference across that component times the output current. So the correct answer is C. So what is the equation for calculating power dissipated by a series linear voltage regulator? Correct answer C. Voltage difference from the input to output multiplied by output current. So just for clarity, because that sounds like an important equation, it's voltage difference from input to output. So obviously you subtract there, and then multiplied by the output current. And that's how you would know your power dissipated. There we go. All right. Do a couple more questions here, finish out this page. So, what is the function of the pass transistor in a linear voltage regulated circuit? Regulator circuit, sorry. A, permits a wide range of output voltage settings. B, provides a stable input impedance over wide range of source voltage. C, maintains nearly constant output impedance over wide range of load current. Or D, maintains nearly constant output voltage over a wide range of load current. A very simple voltage regulator typically consists of a Zener Diode reference voltage in parallel with a load resistance. However, such a simple circuit has practical power limitations, as the Zener could dissipate about 10% of the load, 10% of the load power. The effect of the Zener diode can be amplified greatly by using a large and relatively inexpensive pass transistor, which uses the Zener diode merely as a reference voltage while using its own current gain to control the current through the load and hence the output voltage. So the correct answer is D. Yeah, the equations are always tough, and I've heard it's the part of the hardest part about this. The extra is it's a lot more of the equations and technical side than what we saw general or tech. So, what is the function of the pass transistor in the linear voltage regulator circuit? The correct answer is D. Maintains nearly constant output voltage over a wide range of load current. But yeah, that's my biggest, I think, hurdle, is I want to make sure that I know a lot of those equations and understand a lot more of this. I want to take it and pass it and be done with it. But I agree with you, D. It definitely is the hardest part to remember all. All right, here. Next question. Which of the following types of linear voltage regulator places a constant load on the unregulated voltage source? A constant current source. B, a series regulator. D, a shunt current source. Or D, a shunt regulator. In circuits where the load on the unregulated input source must be kept constant, we use the slightly less efficient shunt regulator. These can sometimes get quite warm and usually mounted to the chassis of the equipment, which acts as a heat sink. So the correct answer is D. So which of the following types of linear voltage regulator places a constant load on the unregulated voltage source? D, a shunt regulator. And last question on this page, and then we'll kind of wrap things up. What is the purpose of the Q1 in the circuit shown in figure E7-2? So there's E7-2. Going to show it on screen here. That's our figure that it's talking about. You got Q1, D1 here. R1 here is C1 over 4,000, C2 over 4,000 there. Then we got C3 over 0.01 at R2. And up here you got plus 12, plus 25. Hopefully that kind of clarifies what we're looking at there. A, it provides negative feedback to improve regulation. B, it provides constant load for the voltage source. C, it controls the current supplied to the load. Or D, it provides D1 with current. Q1 is a transistor that can handle greater current than the Zener diode. They sometimes call this transistor series pass, and it is used to control the current supplied to the load. So the correct answer is C. So Q1 is used to control the current supplied to the load. So what is the purpose of Q1 in the circuit shown in figure E7-2? Correct answer is C. It controls the current supplied to the load. And that puts us somewhere around a dozen questions or so for the night. And we kind of keep it that way just for attention span wise for myself and anybody watching. It could get a little dry. We do too many more than that. And kind of lose interest right quick. And I, for one, don't want to do that to myself. Transition back over here. But I appreciate everybody studying along with me. Thank you to Greg and Dee, both in the chat there, with a little bit of conversation. I appreciate that, definitely. Lost my train of thought there for a second. But thanks to both of you with some comments in the chat. And with that, we'll end it for the night. When will I be doing the next one? I try to do it every couple weeks and try to do something in between, but it just depends on what I have going in the meantime. But I try to keep it fairly regular, and we'll try to have something where it's shown on the channel that it'll be on. Some of them I'll just actually record and upload, and every once in a while I'll do it live, kind of like tonight. So it's kind of a back and forth, but I try to keep it a fairly regular upload or question pool coming. So at least till the book is done, we're probably about half, maybe just over, of the question pool. So yeah, I'm not sure as far as that goes, but hopefully that answered your question, Dee. So with that, I appreciate everybody in, and I want to say thanks to all, and get on the air. 7-3.